In April 2026, the warning coming from the American West was not simply that there was less water. It was that the system people had spent decades building around water was becoming harder to predict. The Colorado River Basin, a network of rivers, reservoirs, aquifers, farms, cities, and infrastructure serving more than 40 million people, was facing a combination of conditions that would have been difficult to imagine only a generation ago. The Bureau of Reclamation reported that long-term drought had pushed Colorado River system storage to about 36% of capacity. Then came another problem. The basin experienced its lowest winter snowpack on record, followed by record-breaking March heat. That combination matters because, in the American West, snow is not just scenery. It is a reservoir in disguise. During winter, snow accumulates in mountain ranges. When temperatures rise in spring and early summer, that snow gradually melts, feeding rivers and reservoirs at the time when farms, cities, and ecosystems need water most. But when there is less snow, and when heat arrives unusually early, that natural timing system starts to break down. And that is where the story becomes much bigger than a drought. Because the United States is not facing one single water problem, it is facing several different problems that are beginning to collide. There is the obvious one: not enough water in some of the places that depend on heavily managed rivers. There is groundwater depletion beneath agricultural regions. There are aging pipes and treatment systems. There are contaminants that can remain in water for years. And there is a financial problem hiding underneath all of it. Even when a community knows exactly what needs to be fixed, paying for it can be extraordinarily difficult. The Environmental Protection Agency has estimated the 20-year national need for drinking water infrastructure at roughly $629 billion. Its assessment also identified approximately 9.2 million lead service lines across the country, with replacement costs estimated at $50 billion to $80 billion. So the American water crisis is no longer just a story about a dry river. It is becoming a story about the reliability of an entire system. And that distinction is crucial, because when people hear water crisis, they often imagine the most dramatic version of scarcity: a reservoir disappearing, a riverbed drying out, or a city running out of water. Those things can happen. But a modern water crisis can also arrive quietly. A well may have to reach deeper than it did a decade earlier. A utility may discover that a treatment plant needs an expensive upgrade. A community may learn that an unwanted chemical has entered its water supply. A farmer may discover that groundwater accumulated over thousands of years is being withdrawn much faster than nature can replace it. None of those events necessarily produces a single dramatic image. Together, they can fundamentally change the security of a region. And scientists have been documenting one of the clearest examples of that transformation in the Colorado River Basin. A 2025 USGS assessment found that average stream flow in portions of the upper Colorado River headwaters declined by roughly 20 to 23%. When researchers compared the prolonged drought period from 2000 to 2022 with the wetter period from 1982 to 1999. Average surface runoff also declined by roughly 24 to 31% in the studied headwater regions. That does not mean the river is simply going to vanish. It means something more complicated. The amount of water entering the system has changed, and the demands placed on that system have not disappeared with it. In fact, the Colorado River is already at the center of an enormous political and scientific negotiation. The current operating framework for the river's major reservoirs expires at the end of 2026, and as of February 2026, the 7 basin states had not reached full consensus on what comes next. The federal government was moving forward with a process intended to establish new operating guidelines. That deadline is not just bureaucratic. It is a signal that an old assumption is being tested, that the water system designed for the American West can continue operating under conditions that increasingly resemble a different climate. And there is another layer that makes the situation even more difficult: the water beneath the ground. For decades, groundwater has functioned as a kind of emergency reserve. When surface water is scarce, wells can keep farms productive and communities supplied. But groundwater is not an infinite backup tank. Some aquifers recharge quickly, others recharge extremely slowly. And once a region begins depending heavily on groundwater to compensate for unreliable surface supplies, the solution to one problem can gradually create another. The Colorado River Basin offers a striking example of this hidden depletion. Research summarized by the U.S. Geological Survey shows that long-term drought and water use have reduced supplies across the basin, while scientists continue investigating how groundwater, snow, wildfire, evaporation, and changing runoff interact. This is the mystery at the center of the new phase of America's water crisis. What happens when the traditional fixes stop working as reliably as they once did? For a long time, the answer to a dry year was relatively straightforward. Store more water, build more infrastructure, drill deeper, move water from somewhere else, treat it, conserve it. But every one of those strategies has limits, and those limits are beginning to appear at the same time. The most important question, then, is not whether America has enough water on the planet. It is whether the country can reliably deliver the right amount of safe water to the right places, year after year, while the physical conditions underneath that system are changing. To understand why that question has become so urgent, we have to look beneath the reservoirs and beyond the headlines. Because the most important part of America's water crisis may not be the water we can see. It may be the water we've been quietly using up underground. That hidden water is groundwater. And for millions of Americans, it has become the difference between having a reliable water supply and having almost none at all. Across the Great Plains, California's Central Valley, Arizona, and other heavily irrigated regions, the water crisis can look strangely normal from the surface. Fields are green, crops are growing, pumps are running. But beneath some of these landscapes, the balance sheet is moving in the wrong direction. Groundwater can be replenished, but not necessarily at the speed humans remove it. Rain and snowmelt can eventually reach underground formations, but in some aquifers, that process takes years, decades, or far longer. A well can keep producing water even while the underground reserve supplying it is shrinking. And nowhere is that tension more consequential than in the High Plains Aquifer, one of America's largest groundwater systems. It stretches beneath parts of 8 states and supports enormous agricultural regions where rainfall alone cannot reliably sustain crops. But its condition is not uniform. Some areas have remained relatively stable. Others have experienced substantial declines. The U.S. Geological Survey has documented major long-term groundwater level changes, including severe depletion in parts of the southern and central High Plains. When groundwater falls, the problem may not arrive as a sudden collapse. A pump has to work harder. A well may need to reach deeper. Energy costs rise. Eventually, the amount of water available can become economically or physically impractical to extract. That creates a dangerous illusion. The system can appear resilient because the water is still coming out of the ground. But the reserve may already be shrinking, and groundwater is only one part of the equation. The other is heat. Higher temperatures increase evaporation from soil, vegetation, rivers, reservoirs, and snow. They can also change when snow melts. That matters enormously in mountain watersheds. Imagine 2 winters with similar precipitation. In one, much of that precipitation falls as snow, remaining stored in the mountains until spring. In the other, warmer conditions produce more rain, earlier snowmelt, and faster drying. The total precipitation might not look dramatically different, but the amount of water eventually reaching rivers and reservoirs can be. Scientists have observed this changing relationship in the Colorado River Basin, where runoff efficiency has declined. In simple terms, the landscape is producing less river water from a given amount of precipitation. Research points to several interacting causes, including higher temperatures, declining snowpack, soil moisture changes, and vegetation. This is why the word drought can sometimes be misleading. Drought sounds temporary. A dry period begins, rain eventually returns, and the system recovers. But climate-driven warming can alter the conditions under which that recovery occurs. A wet year can still be a wet year. It simply may not refill the system as completely as it once would have. The Colorado River shows why that matters. The Southwest has experienced more than 2 decades of unusually dry conditions. A major 2022 study found that 2000 to 2021 was the driest 22-year period in at least 1,200 years for the region examined, based on tree ring evidence. The researchers also estimated that human-caused warming substantially intensified the drought. Natural droughts happened long before modern climate change. The difference is that today's warming is occurring on top of that natural variability. A dry year removes water. Heat increases losses. Low soil moisture makes landscapes more vulnerable. Reduced snowpack changes runoff timing. And human demand continues. The result is not one problem, but a network of problems. Climate affects snow. Snow affects runoff. Runoff affects reservoirs. When surface water becomes less reliable, groundwater pumping can increase, and increased pumping can put further pressure on aquifers. But America's water crisis is not limited to the dry West. Some of the country's most serious water problems occur in places where water appears abundant. Because having water is not the same as having usable water. A community can sit beside a major river and still struggle to provide safe drinking water. The infrastructure beneath American streets is aging. Drinking water systems depend on treatment plants, pipes, pumps, storage tanks, and service lines, many of which were built decades ago. And infrastructure can fail without announcing itself. A bridge collapse is visible. A deteriorating water main is not. The EPA estimates that the United States has roughly 9.2 million lead service lines. Replacing them is a massive logistical and financial challenge, requiring utilities to locate the lines, coordinate construction, and fund the work. Then there are contaminants such as PFAS, a large family of human-made chemicals that can persist in the environment and have been associated with health concerns. Removing contaminants can require specialized treatment, which means additional money, energy, equipment, and long-term monitoring. This creates a second water paradox. A country can have enough water physically available while still lacking enough affordable, clean, dependable water. And the burden is not distributed equally. A large metropolitan utility may have millions of customers over whom it can spread the cost of a major infrastructure project. A small town cannot. The treatment plant still needs maintenance. The pipes still need replacement. Testing still costs money. Engineers still have to be paid. But there may be only a few thousand customers covering the bills. So America's water crisis is becoming several crises at once. A climate problem, a groundwater problem, an infrastructure problem, an environmental problem, and a financial problem. And these problems are colliding with a system designed around an older assumption. For much of modern American history, the country behaved as though water could be engineered into submission. Build a dam, build a canal, drill a well, move the water, treat the water, store the water. And for decades, those strategies worked remarkably well. But they were designed around a world in which the underlying supply was more predictable. Now the challenge is different. The system is being asked to manage not only scarcity, but uncertainty. A reservoir can be designed around expected river flows. A pipeline can be sized for projected demand. A treatment plant can be built around expected contaminant levels. But what happens when the baseline itself keeps shifting? That is the question now hanging over the American West. And it may explain why the next stage of the crisis will not necessarily arrive as one catastrophic event. It could arrive as a long sequence of years in which the system repeatedly falls just short of the conditions it was designed to handle. And that changes the central question. The problem is no longer simply whether America has enough water. The harder question is whether the systems built to capture, store, move, and clean that water can keep functioning when the conditions they were designed around are changing. To understand why, we need to look at one of the most important misconceptions about the American West. People often imagine water scarcity as a simple equation. There is a certain amount of water. There are a certain number of people. If demand becomes too high, the solution is to reduce demand or find another source. But rivers do not behave like bank accounts with predictable deposits. The amount of water available can change dramatically from one year to the next, and climate determines more than just how much precipitation falls. It influences where precipitation falls, whether it becomes snow or rain, how quickly snow melts, how much water evaporates, and how much eventually reaches a river. That is why the Colorado River is such an important case study. Its enormous network of reservoirs and infrastructure was built around historical assumptions about how much water the river could reliably provide. The problem is that the historical record is no longer a perfect guide to the future. Tree rings show that the Southwest experienced severe droughts long before modern climate change. But the recent period is different. Human-caused warming is increasing temperatures across a region already vulnerable to drought. The result is sometimes described as hot drought. The landscape can become drier, not only because less precipitation arrives, but because more available moisture is pulled back into the atmosphere. That helps explain why precipitation alone can be a misleading measure of water security. Imagine a watershed receiving the same amount of precipitation it did decades ago. If temperatures are higher, more water can be lost through evaporation and plant transpiration before reaching a reservoir. This is why scientists study the entire water cycle rather than simply counting inches of rain and feet of snow. And the consequences can compound. When reservoirs fall, water managers have fewer options. When surface supplies decline, some users turn to groundwater. When groundwater levels fall, wells become more expensive to operate. Meanwhile, environmental systems are also competing for water. Rivers are not just pipes carrying water toward cities. They support fish, wetlands, wildlife, forests, recreation, and ecosystems that can be damaged when flows become too low or temperatures rise. This creates a conflict with no easy technical solution. Every gallon allocated to one purpose is a gallon that may not be available for another. And that brings us to a critical point about America's water infrastructure. Infrastructure can move water. It cannot manufacture a river. A new pipeline can redistribute existing supplies. A larger reservoir can store water when it is available. A deeper well can reach water underground. But none of these creates an unlimited supply. That is why one of the most consequential debates in the West is not simply about building more infrastructure. It is about deciding who receives water when there is not enough for everyone to receive what the old system promised. The Colorado River makes this conflict unusually visible. 7 states, dozens of tribes, major cities, agricultural districts, and Mexico all depend on it. The river is divided between an upper basin and lower basin, with legal agreements governing how its water is shared. Those rules were developed over generations. But the river's physical reality has been changing faster than the political framework. That is why the expiration of the current operating guidelines at the end of 2026 matters so much. The states and federal government are trying to determine how the river should be managed afterward. The challenge is that there is no solution that simply makes the shortage disappear. If one group receives more water, another may receive less. If cities conserve more, farms may still face reductions. If agriculture pumps more groundwater, aquifers may decline faster. Every decision moves pressure somewhere else, and this is where the water crisis becomes political. But politics is only part of the story. There is another factor that makes the future particularly difficult to predict. Groundwater and surface water are connected. A river is not one completely separate resource, and an aquifer another. Water can move between them. A pumping well can reduce groundwater that would otherwise feed a stream. A river can also recharge an aquifer under the right conditions. That means a decision made underground can affect a river on the surface. This connection becomes increasingly important as groundwater pumping expands. The High Plains Aquifer illustrates the danger. In parts of the aquifer, decades of irrigation have dramatically reduced groundwater levels. As groundwater declines, some streams can also lose part of the groundwater contribution that helps maintain their flow. Eventually, agriculture may have to adapt because the water simply cannot be extracted at previous rates. And agriculture matters enormously here. Irrigated farming consumes a huge share of water withdrawn in many western states. That does not mean farmers are simply wasting water. It means agriculture developed around supplies considered dependable enough to support particular crops and economies. Changing that system is not as simple as telling people to use less. A farm is land, equipment, workers, loans, food production, processing, transportation, and an entire local economy. Reduce water availability, and the consequences can spread far beyond the farm. This is why water policy becomes so contentious. The scientific question is, how much water is actually available? The economic question is, what happens to communities if that amount is reduced? And the political question is, who should absorb the reduction? Those questions become more urgent when physical conditions change faster than institutions can adapt. But the West has another hidden vulnerability. In some regions, heavy groundwater pumping can cause land to sink. The process is called land subsidence. When water is removed from certain underground sediments, those sediments can compact. In parts of California's Central Valley, subsidence has become a major infrastructure concern. Some areas have experienced substantial sinking because of long-term groundwater extraction, particularly when surface water supplies were limited. This creates a feedback loop. Water scarcity causes more groundwater pumping. Pumping causes subsidence. Subsidence can damage canals, roads, bridges, wells, and other infrastructure. Damaged infrastructure makes water delivery more difficult, and that can increase pressure on groundwater. The crisis begins feeding itself. This is why water shortage does not fully describe what is happening. A river shortage becomes a groundwater problem. A groundwater problem becomes an energy problem. An energy problem becomes an agricultural problem. An agricultural problem becomes a food and economic problem. Eventually, all of it becomes political. But there is an important misconception to clear up. None of this means the United States is about to run out of water. That is not what the evidence shows. America contains enormous quantities of fresh water. The challenge is that water is unevenly distributed, expensive to move, expensive to treat, and increasingly variable in some regions. That distinction changes what solutions make sense. The answer is not simply to find one giant new source. It is to manage the system differently. That can mean conservation, replacing leaking infrastructure, recycling wastewater, improving irrigation, protecting groundwater recharge areas, changing crops, and planning around permanently different water conditions. Yet even promising technologies have limits. Desalination can produce fresh water from seawater, but requires substantial energy and creates concentrated brine that must be managed. Water recycling can expand usable supplies, but treatment systems are expensive and require public trust. New reservoirs can capture water, but depend on rivers filling them. Conservation can reduce demand, but additional savings become increasingly difficult. No single technology solves the fundamental problem. The system needs many solutions working together, and that may be the biggest revelation of all. The United States did not build its modern water system around permanent uncertainty. It built much of it around the expectation that scarcity would remain manageable. Now that assumption is being tested. The future may not be defined by one dramatic day when the taps suddenly stop. It may be defined by a gradual loss of reliability, a reservoir that does not refill quite as much, a well that must be drilled deeper, a farm that can no longer grow the same crop with the same amount of water, a town facing a treatment bill it cannot easily afford, a river becoming warmer and less reliable. Each change can look manageable by itself. Together, they represent something much larger. A transition from a water system built for predictable scarcity to one operating under persistent uncertainty. And the consequences extend far beyond the Colorado River. Because the next question is no longer what happens when one region experiences drought. It is what happens when water stress begins affecting the country's economy, infrastructure, food production, and communities at the same time. That is where the real stakes of America's new water crisis begin to emerge, and that is where the water crisis becomes something much larger than a problem for the American West, because water is connected to almost everything: food, electricity, housing, industry, public health, and the economy itself. When water becomes less reliable, the consequences move through the systems that depend on it. Start with food. California's Central Valley produces a remarkable share of the fruits, vegetables, and nuts consumed in the United States. Much of that agriculture depends on irrigation, using both surface water and groundwater. When surface supplies become unreliable, farmers can compensate by pumping more groundwater. But that solution has limits. A farmer may have to reduce the amount of land planted. A crop may become less attractive. An orchard that took years to establish may become difficult to maintain. Local businesses, transportation, and food processing industries can feel the effects too. The point is not that America is about to run out of food. It is that water availability can influence what is economically possible to grow, where it is grown, and how expensive production becomes. And that is already changing how some communities think about water. For decades, water policy often focused on increasing supply. Today, many communities are increasingly focused on managing demand. Reducing water use sounds simple, but the largest reductions may require changes in agriculture, industry, landscaping, groundwater management, and municipal infrastructure. That is why some of the most important water decisions happen far away from kitchen sinks. They happen in state legislatures, water districts, courtrooms, farm fields, and underground. The Colorado River is once again the clearest example. The river's 7 basin states have spent years negotiating how to divide a shrinking and increasingly uncertain supply. The current rules expire at the end of 2026. That deadline forces an uncomfortable reality into the open. The old agreements were written for a river that was often assumed to be more generous than the long-term average could reliably sustain. Now the states must negotiate under conditions where there may simply be less water available. And every solution creates winners and losers. Reducing agricultural allocations can protect cities, but pressure rural economies. Reducing urban use can preserve supplies, but becomes increasingly difficult after years of conservation. Holding more water in reservoirs can provide security later, but means someone may receive less water now. There is no button that resets the river to its 20th century conditions. This is why scientists and water managers increasingly talk about resilience rather than simply recovery. Recovery assumes the system will eventually return to what it was. Resilience means preparing it to function when conditions remain different. That means communities cannot necessarily plan around the assumption that the next wet period will erase the last drought. They may need to plan around a permanently different baseline, but even that has limits. Scientists can identify broad trends and estimate how warming is likely to affect snowpack, evaporation, drought risk, and runoff. But they cannot tell a city exactly how much water it will have on a particular day 10 years from now. Weather remains variable. Climate projections describe probabilities and ranges, not precise schedules. That uncertainty can make planning politically difficult. A mayor may be asked to approve an expensive water project because scientists say future shortages are becoming more likely. But taxpayers see the bill immediately, while the benefits may not appear for decades. That is one reason infrastructure is central to the story. The United States has an enormous water infrastructure network, but much of it is aging. The EPA's national assessment estimated hundreds of billions of dollars in drinking water infrastructure needs over a 20-year period. And that is only part of the system. Wastewater plants need upgrades. Dams and reservoirs require maintenance. Canals need repairs. Pipes leak. Treatment technology must adapt to new contaminants. The challenge is not simply finding money. It is deciding where to spend it first. A leaking pipe may waste huge quantities of treated water. A treatment plant may serve a community that cannot afford major upgrades. A rural water system may have serious needs, but too few customers to spread the cost. And some failures are difficult to predict because the infrastructure is underground. This creates another dangerous characteristic of the water crisis. It can remain invisible until the moment it becomes expensive. Consider a water main. It can deteriorate gradually without making headlines. Then a break occurs. A road floods. Businesses close temporarily. Water service is interrupted. Repairs have to happen immediately. Preventing that failure might have cost less than repairing it. But prevention is harder to sell because nothing dramatic happens when prevention succeeds. The same principle applies to groundwater. If a community reduces pumping today to protect an aquifer decades into the future, the benefit is difficult to see. But if it waits until wells begin failing, the cost can be far higher. This is why water management is fundamentally a problem of time. Decisions made today can determine what options remain available years from now. And there is another issue that makes the timeline even more complicated. Water quality. A community can have plenty of water and still have a crisis if that water cannot be safely used. PFAS have become a major example. These chemicals have been widely used in industrial and consumer applications, and some can persist in the environment for long periods. Federal regulators have established drinking water standards for certain PFAS, while communities work to understand where contamination exists and how to remove it. But detection is only the beginning. Once a contaminant is found, someone has to pay for testing, treatment, monitoring, and infrastructure. And the problem becomes more difficult when the affected community has limited financial resources. This is where the water crisis reveals an issue of inequality. Two communities can face the same physical problem, but have radically different abilities to respond. A wealthy city may build an advanced treatment system. A small rural community may struggle to replace a single aging pipe. A major agricultural district may have sophisticated groundwater monitoring. A poorer area may lack the personnel to collect enough data. Water scarcity, therefore, does not create the same consequences everywhere. It amplifies existing vulnerabilities. And this is perhaps the most important thing to understand about the next phase. The crisis will not look identical across the United States. In one place, the defining problem may be groundwater depletion. In another, contamination. Some communities may face aging infrastructure. Others may face floods and stormwater problems rather than scarcity. And some will experience several pressures simultaneously. The United States is not simply becoming drier. Different regions are experiencing different water extremes. Some areas face prolonged drought. Others experience increasingly intense rainfall. A warmer atmosphere can hold more moisture, increasing the potential for heavy precipitation. But heavy rainfall does not automatically solve water shortages. Rain can arrive too quickly. It can run off instead of infiltrating the ground. It can overwhelm drainage systems. It can cause flooding while doing surprisingly little to replenish a depleted aquifer. A place can experience a major flood and still face a water shortage later. Too much water at the wrong time is not necessarily useful water. And that brings us back to the fundamental problem. The challenge is not simply water quantity. It is timing, location, quality, storage, infrastructure, and access. The country may have enormous quantities of water somewhere. The question is whether that water is available where and when people need it, and whether it can be delivered safely and affordably. That is why the next decade could be so important. The choices being made now will determine whether water systems become more adaptable or remain locked into assumptions from a different era. There are reasons for cautious optimism. Water recycling is expanding. Agricultural technology is improving. Groundwater monitoring is becoming more sophisticated. Cities have achieved major conservation gains. Infrastructure investments are increasing. But none of these solutions removes the underlying pressure. The physical system still sets the limits. And that leads to the final question. What happens if those limits arrive faster than institutions can adapt? The answer is unlikely to be one nationwide disaster. It will probably be a collection of increasingly difficult decisions. Which farms continue receiving water? Which communities receive infrastructure funding first? Which groundwater basins are protected? How much should households pay? How much should industries pay? How much water should remain in rivers for ecosystems? And who gets to decide? Those questions will define the next phase of America's water story, because the greatest danger may not be that the country suddenly runs out of water. It may be that water becomes increasingly unreliable, expensive, and politically difficult to distribute. And if that happens, the most important resource will not simply be water itself. It will be the ability to adapt before the choices become emergencies. And that is the real challenge facing the United States. Not a single moment when every reservoir goes empty. Not one day when the entire country runs out of water. Something more complicated, a gradual loss of reliability. The water system can still function while becoming harder, more expensive, and more politically difficult to maintain. The United States has enormous water resources, but water does not exist where it is needed simply because it exists somewhere in the country. It has to be captured, stored, moved, treated, monitored, and paid for. Every one of those steps has limits. The evidence now points toward a future in which those limits will be tested more often. In the Colorado River Basin, the immediate challenge is determining how the river will be managed after the current operating guidelines expire at the end of 2026. The 7 basin states, federal officials, tribes, cities, farmers, and other water users all have different priorities. There may not be enough water to satisfy every historical expectation. That means the next agreement will not simply divide water. It will reveal what the region believes about its future. Does it assume today's shortages are temporary? Or does it plan for a river system that may remain fundamentally different from the one previous generations knew? That distinction could shape decisions for decades. But the Colorado River is only one part of the story. Across the country, groundwater is becoming more important. Groundwater can provide an essential buffer during dry periods. But if pumping consistently exceeds recharge, the buffer eventually becomes smaller. The effective strategy is not simply to pump more. It is to understand the aquifer, measure withdrawals, protect recharge, and determine how much water can be used without destroying the resource communities depend on. Groundwater often crosses property and political boundaries. A well drilled on one property can affect water beneath another. A decision by one community can influence a shared aquifer. That is why monitoring matters. You cannot manage a resource effectively if you do not know how quickly it is changing. The same principle applies to infrastructure. Aging pipes, treatment plants, reservoirs, canals, and pumps cannot all be replaced at once. Communities have to determine which failures pose the greatest risks and invest before emergencies force their hand. That requires thinking decades ahead. A repaired pipe rarely makes national news, but that is what resilience looks like, preventing the crisis before it becomes visible. There are technologies that can help. Water recycling can turn wastewater into a valuable resource. Improved irrigation can produce more agricultural output with less water. Advanced monitoring can detect leaks and track groundwater changes. Desalination can provide fresh water in coastal regions, where its energy and environmental costs are manageable. None is a magic solution. But together, they can increase the number of options available to communities. And options become valuable when water supplies are uncertain. There is another solution that receives less attention because it is less technological. Conservation. Cities have already shown that demand can change. Landscaping can use less water. Leaks can be repaired. Agricultural practices can become more efficient. Water can be reused rather than discarded. But conservation also has limits. Eventually, communities have to decide what they are willing to change. That may mean different crops, landscapes, water prices, and expectations about how much water can reliably be available. Because water policy is ultimately about people. A river does not care which state line it crosses. An aquifer does not recognize a county boundary. But governments do. Water rights do. Budgets do. And communities do. Scientists can measure declining groundwater levels. They can reconstruct droughts using tree rings. They can model snowpack and runoff. They can estimate how warming changes evaporation. But science cannot decide who should receive water when supplies are insufficient. That is a social and political decision. Farmers are protecting livelihoods. Cities are protecting residents. Tribes are protecting water rights and sovereignty. Industries are protecting economic activity. Environmental groups are protecting ecosystems. Every side can point to legitimate needs. That is why the next phase of America's water crisis will not be solved by a single announcement or enormous infrastructure project. It will require thousands of decisions. Some will be local. Some will be statewide. Some will involve federal agencies. Others will involve negotiations across entire river basins. And many will happen long before the public realizes there is a crisis. That may be the most important lesson. A water crisis does not begin when the taps stop. It begins when the choices available to prevent that outcome start disappearing. A community that still has water today may face a serious problem if its aquifer is declining, its pipes are deteriorating, or its treatment system is approaching the end of its useful life. A reservoir that still contains billions of gallons may be a warning sign if inflows remain below historical expectations. A farm can remain productive while depending on groundwater that cannot be sustained indefinitely. The visible condition of the system can therefore be misleading. And that brings us back to the question from the beginning. What happens when the traditional fixes stop working as reliably as they once did? The answer is not that America suddenly becomes a desert. It is that water becomes a constraint. A constraint on where people can build. A constraint on what farmers can grow. A constraint on infrastructure budgets. And eventually, a constraint on political choices. But there is an important reason not to view this story as inevitable collapse. The United States has enormous technical capacity. It has experienced water engineers, scientists, farmers, utility workers, researchers, and communities that have already shown that demand can change and systems can adapt. The country has also invested billions of dollars in water infrastructure. What happens next depends partly on whether that investment is used reactively, after systems fail, or strategically, before failures become emergencies. And there is still uncertainty. Scientists cannot tell us exactly how every river, aquifer, or reservoir will behave in the coming decades. That uncertainty should not be mistaken for ignorance. We know warming is changing the water cycle. We know some major aquifers have been depleted. We know aging infrastructure requires enormous investment. We know contaminants can create expensive long-term challenges. And we know water demand is not disappearing. What remains uncertain is how quickly these pressures will combine, and how effectively institutions respond. That is why the most important number may not be the level of a single reservoir. It may be the amount of time communities have to adapt before their options become much more expensive. The United States still has choices, but choices become narrower when action is delayed. And perhaps that is the real meaning of the new phase of America's water crisis. The danger is not simply scarcity, it is losing flexibility. When groundwater is plentiful, there are many choices. When reservoirs are full, there are many choices. When pipes are reliable and treatment systems are modern, there are many choices. But as those margins disappear, every decision carries greater consequences. The water crisis will not necessarily arrive as a single dramatic event. It may arrive quietly, through thousands of smaller changes that gradually reshape the country. A deeper well, a smaller snowpack, a lower reservoir, a repaired pipeline, a more expensive water bill, a field left unplanted, a treatment system upgraded before it fails. Each one seems like an isolated story. Together, they describe a nation learning that water security is not something that can simply be assumed. It has to be maintained. And that brings us full circle to the opening idea. The American West is not running out of water in one sudden moment. The deeper problem is that the old predictability is disappearing. The snow that once arrived reliably may melt earlier. The river that once supplied a familiar amount may deliver less. The groundwater reserve that seemed endless may decline. The infrastructure that quietly delivered water for generations may require billions of dollars to remain dependable. Together, they force a different question. Not, will America run out of water? But, how much uncertainty can America's water system absorb before the way people live, farm, build, and grow has to change? We do not know exactly where that threshold lies, but the evidence suggests the country is moving closer to it, and the decisions being made now will determine whether that transition becomes managed adaptation or a series of emergencies. The water is still there. The question is whether America can keep making it available, safe, affordable, and reliable, before the choices become emergencies. If this documentary changed the way you think about water, consider subscribing for more evidence-based stories about the systems shaping the future.